going to move on to our final speaker now, Huan, who's going to present Modeling Post-Disaster Business Recovery, a semi-Markov estimation framework.
Thank you very much for the introduction. Now I will share my screen. Yeah. Can you see my screen? Okay.
Yes. Yeah.
Yeah. Thank you very much. Hi, everyone. Thank you for being here. My name is Huan Liu, and I am now working as a program-specific assistant professor in Kyoto University. So thank you for IDRiM committee for providing this opportunity for the presentation. And today I would like to introduce the research modeling post-disaster recovery under a semi-Markov framework. So this research is co-authored with Professor Tatano and Professor Kachitani. So the presentation is going to be introduced from these 5 parts. It's known to us that we are facing with an increasing disaster occurrence frequency and also the expanding disaster impact and losses caused by disaster. Under this situation, many studies have been done in managing and reducing risk. On the other hand, since we cannot avoid risk, so building resilience is another effective solution for us to reduce economic losses caused by disaster. As shown in the figure here, economic resilience can be defined from 2 dimensions, resistance and recovery. Resistance defines the ability of system to absorb the shocks immediately after disaster, and the ability to recover describe the speed and the recovery time of the system to recover from the disasters. So many studies have been done from the macroeconomic perspective, but very few evidence have been provided from the individual firm level. So in our research, we focus on the resilience analysis from industry sector's perspective. So here, production capacity rate, which is the maximum productivity that a firm could produce if all the resources are utilized in the post-disaster. So from the perspective of industry sectors, the triangle area here actually represents the production capacity loss rate in industry sectors caused by disasters. So as we introduced, the resilience can be defined from 2 dimensions. First is the resistance. So resistance can be impacted by the hazard intensity and also by the lifeline disruptions. So in our previous research, we have developed and proposed the lifeline resilience factors, which can estimate the remaining percentage of production capacity for firm when lifeline disruptions occurred. Compared with previous study, which are derived from the hypothetic disaster business survey data or expert opinion-based estimations, in our research, we propose a modeling framework which can estimate the lifeline resilience factors from the empiric post-disaster data. And also, we derive a set of lifeline resilience factors by applying to the 2011 Great East Japan earthquake dataset. Here is the resistance, like lifeline resilience factors we derived from the 2011 Great East Japan earthquake. For example, the electricity, if the electricity disrupted, then only 2.3% of production capacity remained after in industry sectors. So this is the lifeline resilience factors describe the importance of lifeline in supporting the productivity. We also compare the estimation results with the current references from the hypothetic disaster survey and expert opinion-based estimation, ATC 25, and result shows consistency. So if you have some interest in the resistance analysis, please kindly refer this paper we published in Earthquake Spectrum in 2020. So today's presentation, I would like to focus on the recovery analysis in industry sectors. Knowing the recovery from of industry sectors can help us to estimate the losses caused by disasters, and also understanding recovery can help us to better preparation and mitigation in case of future disasters. Current studies also identify the recovery from the macro perspective. However, the dynamic resilience from firm level perspective has not been well addressed. Meanwhile, so far, the current methodology, for example, survival analysis or regression analysis, they did not include the impact of inference factors and also the uncertainty in the recovery process. Therefore, semi-Markov model can capture the uncertainty and the randomness of a stochastic process, but not being applied in the field of post-disaster recovery. To facing with this situation, the challenge to modeling the recovery is how we could incorporate the inferencing factors and adjust the uncertainty in the recovery function. Under this background, in our research, we aim to answer these two questions. First, how resilient are industry sectors in facing of disasters, and how will inference factors affect the resilience in industry sectors? So we will consider different industry sector types, business size and initial damages, and also the lifeline supply, how those factors will impact the recovery. By doing this, we could establish the parametric business recovery function to estimate the recovery process in industry sectors, and we can identify the importance of factors in the recovery function. And with those kind of results, we could provide empiric evidence for business managers and decision makers to build a resilient industry. To achieve this, this is the framework of our research. Immediately after disaster, we have different types of firms from different initial damage. And then by derived the recovery function, we can estimate the recovery curves. So this triangle area represents the losses caused by disasters. And also we incorporate different factors into the recovery function to compare how those factors impact on the recovery. To achieve these objectives, we have 4 steps. First, we will introduce multi-state semi-Markov process and how we want to utilize the Markov process to describe the business recovery process. And then we establish a conditional recovery function, which is conditional on different initial damage. And we solve the parameters by establish and maximize likelihood function. Then we identify how factors impact on recovery function. So here, the figure here in the left side describe the simple semi-Markov process. There are 2 elements in the semi-Markov process that are social time and transition probability. Social time describes how long a system stays in a certain percentage of production capacity state, and the transition probability describes the probability for the firm to move to a higher production capacity rate. For example, in the aftermath of disaster, a firm could start from 25%, and after some time in 25%, he could move to a higher state until for recovery. And also, the initial percentage could also be 50%, and after some time in 50%, maybe the lifeline restored, so the production capacity will transit to a higher state until for recovery. So the property of a semi-Markov process actually match with the process of the post-disaster recovery in industry sectors. So this is why we want to introduce semi-Markov process to describe the recovery process. As we mentioned, there are 2 elements in the semi-Markov state. That is the distribution function we represent at FST, and also the transition matrix. So the probability of transition between states can be represented as a matrix. And on the other hand, we developed the recovery function, which describes the probability of a firm's production capacity exists a certain percentage under time T limit, and conditional on the initial damage, because the initial damage will significant impact on the recovery. So we establish the recovery function conditional on different initial damage. And also, as shown in the figure here, we can see that the total recovery time T actually can be expressed as a sum up of the social time. So by substitute the relationship between the total recovery time and the social time, here we can have the recovery function, which is a function of social time distribution. And to also to select the best fit distribution, we apply the AIC standard to select the best fit distribution for the raw data. And to estimate the parameters in the recovery function, we establish the likelihood function and maximize the likelihood function to get and calculate the parameters. also, we can introduce the influencing factors and express the parameters in the recovery function as a function of different influencing factors to compare how those factors impact on the recovery function. So this is a framework of our modeling the recovery function under the semi-Markov process. So here I want to briefly introduce two case studies. For now, we have applied. The first one is the Kumamoto earthquake, and second one is the 2018 heavy rain event. So this is the Kumamoto earthquakes occurred on April 16, 2016, and with the maximum magnitude 7 main shocks, and has caused huge losses in the Kumamoto prefectures. So this is the hazard intensity of the earthquake and also the disruption of electricity, water, and gas. And the figure on the right side represents the average recovery process of lifelines in industry sectors. So we defined the production capacity state into from 0 to 4 states, where state 0 represents 0% production capacity rate, and 4 represent 100% recovery. And we have the distribution of initial production capacity immediately after disaster. So here's the final result we calculated with the proposed recovery function, and from the result in manufacturing sector and non-manufacturing sector, we can see that in general, a more severe damage can lead to a lower recovery about probability. And also in this case study, firms in manufacturing sector have a higher recovery rate compared to firms in non-manufacturing sector. So overall, the proposed recovery function can estimate the recovery rate in the post-disaster recovery time T. And also we validate the result by compare the observed data set with the estimated result. So the result fits where, which show that the proposed model is promising in implying to estimate post-disaster recovery process in industry sectors. So if you have some interest in this paper, please kindly refer the paper we published on 2021. And then the second case I want to briefly introduce is the heavy rain event after the July 2018. So it's occurred from June 28 to July 8 and has caused huge damages to human beings, buildings, industry, and lifelines. Those are the inundated area in Okayama, and the landslides occurred after the heavy rain in Hiroshima Prefecture. Regarding the losses in industry sectors, around 23 to 30% losses are caused in Hiroshima, Okayama, and Ehime prefectures. And as we can see that the power plants was inundated, and also there were many transportation disruption occurred in the disaster affected area. And we conducted a survey with a total of 1,228 respondents, and more than 52% of firms are affected by the heavy rain in manufacturing sector, and 61.7% of firms suffer from damage in non-manufacturing sectors. So we know that there are different characteristics in terms of different types of disaster. In the earthquake type, we consider the electricity, water, and gas, how those lifeline supply will impact the recovery. However, in terms of the flood disaster, we also want to include the inundation depths and the sediment deposit, how those factors will impact on the recovery process, because we have found severe damage caused by the inundation and also the sediment. And also we would like to compare how transportation disruption will impact the recovery. And we also divide into the production capacity rate into different states to represent from totally stopped and until full recovery. And this is a conditional recovery function, and we estimate the recovery curves conditional on different initial damage until to recover to achieve full recovery. So overall, the conditional recovery curves describe the probability of production capacity recovery rate at any post-disaster time T. In addition, here we compare how inundation depths affect the production capacity rate. So we compare 0 centimeter, 100 centimeter, and 300 centimeter inundation depths, and to show how those change, and also the suffer from sediment and without sediment, the impact on the production capacity rate. So we can compare how many percentage differences can occur under different disaster scenarios. And also, we also compare how different lifeline disruption scenarios, like no disruption, 1 week longer disruption, or 16 days disruption, and with and without transportation disruption, impact on the production capacity loss rate, which is a triangle area showed in the figure in the previous introduction. So we can see that in this flood disaster case, the inundation are severe damaged production capacity rate, and also the lifeline restoration process also severe impact the production capacity loss. And this is like can provide an overview of how many percentage difference of production capacity loss rate under different damage scenarios. So to conclude the presentation, in this research, we established a conditional recovery function under the semi-Markov framework, which can consider the impact of influencing factors and also compare how production capacity loss different under different disaster scenarios, and the effectiveness and application are identified through 2 case studies. And in the future, the result maybe can help to understand disaster risk from the individual firm and industry sector's perspective, and contribute to estimating production capacity loss due to flood disasters. And also, by investing in building more resilient critical infrastructures could significantly reduce losses caused by disasters. So in the future, we also want to statistically compare how the role of resilience options can impact the recovery process, and also the effectiveness of the proposed recovery function under semi-Markov framework will be compared with other types of recovery model to identify the effectiveness of this model. So that's the whole presentation. Thank you very much for your attention. I would greatly appreciate the comments.